So yesterday we started with this one. We did this one in class for example 2. We did this one in class for example 2. I think third period got to this one and finished this one in class, but did not get to this one. So, second period, not third period. So for second period, I'm going to have you guys try this one on your own. And then fifth period, we did get a chance to finish this one in class. So we're going to pick up here on part E, the fifth example in example 2. So there are 4 examples left. So there's E, F, G, and H. What I'm going to do is I'm going to do 2 of them with you, and then 2 of them I'm going to have you guys do on your own. So I'm actually going to do E with you, and I will do G with you. And then I'm going to have you guys do H and F on your own. And I'll create either a video or maybe just post up the solutions to what those would look like on School Loop so that you guys can check your work and make sure that you did it right, and you guys can ask me any questions when you come back on Thursday. So let's start with E. Remember that this is the first derivative of the function. So this is just f of x, and we're looking to graph whatever this is f prime of x, and we're looking to graph whatever f of x is. And again, notice that every single one of these has this word possible in front of it, which means that it's not the only possible graph, but it's one of the possible graphs, depending on if they're all, shifted up or down based on their vertical shifts. But this is one possible graph that we'll be drawing. So just like I told you guys yesterday, the first thing I would look for is everywhere that the first derivative has a 0, because remember, wherever the first derivative equals 0, the original function, f of x, has a horizontal tangent line. And we talked about how that can mean a couple things. Horizontal tangent. So we talked about how that can mean that it has a turning point, and most often it will be a turning point. We can talk about how that could also mean that it's just a flat part of the graph. But any 0 on the first derivative implies that there is a horizontal tangent line. Now notice here that some of them aren't exact, like over here at -4, it's not perfectly at -4, but we're going to estimate it as close as possible to -4 just for ease of the purpose of what we're doing. So notice that here we go from negative y values on this side of -4, and then over here we change to positive y values on this side of -4. So to the right of -4 we have positive y values, to the left of -4 we have negative y values. So this 0 actually is a turning point. So I'm just going to label that. This is a turning point, and I'm going to abbreviate it TP, not toilet paper, turning point. Because it changes from negative to positive, so I know that my graph goes from decreasing to increasing. It happens to be a minimum because it's going from decreasing. Remember, negative values mean the function was decreasing, to increasing because it's positive up here. This one is also a turning point. And it happens to be a maximum because if you look here, we're going from increasing, because remember all these positive y values mean the original function was increasing. And then over here to the right of -1, we have negative y values, which mean my function is decreasing. So we're going from increasing to decreasing. That's a maximum right there. And then last but not least, over here at +4, we have one more turning point. Again, for the same reason as the first one, it's going from decreasing to increasing because it's going from negative y values to positive y values. Now yesterday I had you guys highlight some different stuff. So I had you guys highlight what was above the x-axis versus what was below. So if I do that again here, I have this piece below and this piece below. So I will highlight them in blue to say that's a cold piece. And then we have this piece above and this piece above. So those get highlighted in red to say those are warm pieces. So everything in blue is where f prime of x is less than 0, which means that f of x is decreasing. And I'll highlight that in blue to kind of go with our theme. And everything that's highlighted in red is where f of x is greater than 0, or in other words above the x-axis, which means that f of x is increasing. Oops, that's not a very good way of spelling increasing. There we go. And I'll highlight that in red so you guys can see that that's what corresponds to that. So I know that I have a turning point, I know that I have a turning point here, and I know that I have another turning point here. And again, you can see visually because of the change in color. So because it changes from blue to red or from red to blue, that means that we're going to have a turning point on the graph. Now the question is where, is at -4, do I put the point down here? Do I put it up here? Where am I going to put it? And honestly, you can kind of decide where you want to put it to some extent. So all I know is that -4, -1, and +4 are going to be turning points on the graph of my original function. Now we didn't do this too much yesterday. We didn't care to look into it too much, but you can also actually, from the first derivative, you can actually tell information about the second derivative. And remember how the second derivative tells us about concavity. So this was actually in that chart that we were looking at the other day. But I'm going to create, and you guys can write it somewhere in your notes. I know you don't have a ton of room, so how about I write it up here so you guys can do the same. That way you can keep it organized. I'm going to create a little number line, and I'm going to divide it among these zeros that we just found. So -4 is a turning point, -1 is a turning point, and 4 is a turning point. And I'm just going to put little symbols. So everywhere that we're going to have negative values, so everywhere that it's blue, I'm going to put negative. So to the left of -4, and in between -1 and 4, I have negative values. And then everywhere else where it's red, I'm going to put positive. So it's positive in between -4 and -1. And positive to the right of 4. So notice that I have my little number line up here. So this just tells me that the original function is decreasing, turning point, increasing, turning point, decreasing, turning point, increasing. So I'm actually going to erase these colors that we just drew. And I'm going to show you guys what else this function can tell us that I think will be helpful when we try to graph a possible original function. Alright, so here I kept in mind what we already had figured out. So it's all for naught, or not all for naught, I should say. The fact that I erased it is okay. We still have the information kind of secluded up here, I should say, saved up here, I should say. So the next thing we're going to look at is the concavity. So if this green little number line right here tells us about the first derivative, so this is what's happening with the first derivative, let's create another little number line to tell us about what's happening with the second derivative. So remember, if I take the derivative of this function that I'm tracing right here with my little green finger, if I take the derivative of this function, it's essentially the derivative of f prime of x. Well, what's the derivative of the first derivative? It's the second derivative. So essentially, if you were going to take the derivative of this function, you would get the second derivative. Now, if you remember, and if you guys look over on the wall, the thing I always point to every time I tell you what should you think about when you hear the word derivative, the first thing you should always think about is that the derivative is the slope of the tangent line. So I'm looking for the slopes of the tangent lines. So I'm just going to start drawing some lines in here, and I want you guys to notice what you realize or what you notice about the slopes. So I'll try and do them in different colors, and I'm not going to make them perfect, but you guys get the point. Look at this line. Positive, pretty steep. Okay, what about this one? Still positive, less steep. So again, these tangent lines that I'm drawing are related to the second derivative. So we're going to be finding out some information about the second derivative. So notice that right here, my tangent lines are positive because it's increasing. Okay. All of a sudden, when I get to the top up here, I'll do it in blue so you guys can see this. When I get to the top up here, all of a sudden I have a horizontal tangent line, which means that my derivative is now 0. All right, and then over here, what happens? What happens to my tangent lines over here? They become negative. So notice that now my tangent line is negative. So here's what I want you guys to notice about the second derivative. For this function, remember this function is the graph of the first derivative. Okay, notice that the second derivative is positive, 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 0, negative, 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 0, positive, 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 positive. So, just like the relationship between f of x and f prime of x, the second derivative will be positive wherever the first derivative is increasing. So notice that it's increasing right here, and the derivative tangent lines are all positive. The second derivative will be 0 wherever the first derivative has a turning point. So notice that this has a turning point right here. So the second derivative is 0 at that point. The second derivative will be negative wherever the original function is decreasing. So everything right here will have negative tangent lines. And then again, we get down here to a minimum, a turning point. So the second derivative is going to be 0 here at 1. And then last but not least, we come back up here, and because we're increasing again, now our second derivative is positive. So I'm going to highlight a couple different things that I want you guys to notice. Oops, there we go. Here's what I want you guys to highlight, or here's what I want you to notice. And you might not be able to highlight it on your paper because it's probably a lot to write on there. But I want you to notice that at -3, we have a turning point. So the second derivative will equal 0 at -3 and at +1. So up here I'm going to draw a little number line, -3 and +1. These are zeros on the second derivative. So see this little number line that I just wrote? These are zeros on the second derivative. So -3 is a turning point and 1 is a turning point. So they're going to give me zeros on my second derivative. And remember that on the original function, that tells me that these are points of inflection. So this is a point of inflection, and this is a point of inflection. Alright, so now I'm going to highlight again. I'll do it in different colors so you guys can see. Yellow highlight is where my function is increasing. So if a yellow highlight is where it's increasing, that means that it's concave up because my second derivative is positive. Remember, these are all positive slopes right here and positive slopes right here, which means that my second derivative is positive and positive, which means that my original function is concave up and concave up. And then contrary to that, in between those values, we notice that we have some negatives, which means that all of these values in here are negative, which again, back in turn, means that these values are negative, and my original function is concave down in between -3 and +1. So now that we have information about our first derivative, this is going to tell us where our function is increasing and decreasing, and we have information about our second derivative. This will tell us about where our function is concave up and concave down. We can actually plot the points over here. And again, I really don't care where I'm plotting these values, like -3, +1, who cares where we plot them, as long as they fit into the pattern of how to connect these dots. So let's start over here at -4. Okay. To the left of -4, we're decreasing, so we're going to be coming down like this. So my point should probably be somewhere, I don't know, lower on the graph. So over here at -4, oops, there we go. Over here at -4, I have a point right there. So again, notice that I'm decreasing, and then all of a sudden at -4, I change to increasing, so -4 was a turning point. And then at 1, I change from increasing to decreasing. So over here at 1, I change from increasing to decreasing. So this is going to be a turning point as well. And then last but not least, right here at 4, I change from decreasing to increasing. So I'm going to have another turning point at 4. So notice that I have my 3 turning points here. -4 is going to be a minimum, 1 is going to be a maximum, and 4 is going to be another minimum. And if I try to connect these dots, you guys can see how this pattern for the first derivative makes sense. So it goes from negative to positive to negative to positive. Or in other words, the original function goes from decreasing to increasing to decreasing to increasing. So if I can follow it with my finger, it goes from decreasing to increasing to decreasing to increasing. So now the only thing we care about is connecting it the correct way with the correct points of inflection, things like that. So at -3, we have a point of inflection. So here's -3. There should be a point of inflection right there. I'm going to do these in a different color so you guys can see in a different color. At -3, there's a point of inflection, and it goes from concave up to concave down. So I don't really exactly know where it's going to be, but it needs to somehow fill in the blank. So it's going to go from concave up to concave down. So somewhere in between those two values at -3, we're going to have a point of inflection right there. And then same thing over here at 1. It's going from concave down to concave up. So this is actually a point of inflection as well. It's going to be a weird point of inflection, but it will be a point of inflection nonetheless. Oh, I'm sorry. Did I point this one wrong? This is supposed to be at -1, huh? I'm sorry if you noticed that earlier and I didn't. Let me clarify. See this point right here? See how I put it at +1? It's over here, it says -1. So I'm just going to change this point really quick in case you're unsure about what I'm doing. I'm going to change this point from +1 to -1. So let me erase it. And I'll change it over here to +1. Sorry, opposite, -1. Alright, that makes more sense. So now that I have my point of inflection at +1, now we can actually graph that right here. So we'll put a point of inflection right here at +1. So my black dots are my turning points. So the graph is turning at this point, turning at this point, turning at this point. And my orange dots are my points of inflection. So I'm going to have a point of inflection here and a point of inflection here. So again, we're going to go from decreasing to increasing to decreasing to increasing. And let's see if we can fill in those blanks now. Everything to the left of 3 should be positive, which on the second derivative, which means it's concave up. So let me do this in green. Everything to the left of 3 should be concave up. Hopefully you guys can agree with me that that's concave up and that it goes through the points that we said that it would go through. And again, this is just a possible graph. I put these points randomly. As long as they're on the correct x value, nothing else really matters. The x value is what matters to us. You can't obviously put this point way up here because there's not going to be another turning point. So it just needs to be somewhere in between the two turning points so that you guys can kind of eventually meet there. Then this one right here. In between -3 and +1, it should be concave down because the second derivative is negative. So I'll kind of continue my graph, and this piece should be concave down. All right, so you guys can see that again, that looks like concave down like a frown. And then last but not least, to the right of +1, it turns back to positive again. So if the second derivative is positive, that means that my graph is concave up again. So this last part over here is supposed to look again like concave up. And notice that my graph actually does what it says it's going to do. It goes from decreasing to increasing to decreasing to increasing. And according to the second derivative, it goes from concave up to concave down to concave up. And you guys can see that from the graph. So I want you guys to try that now with the next question. So F, I believe it is. And like I said, I'll put the answer up afterwards. I'll show you guys what they have as the answer, by the way. This is what they put as their answer. Notice that theirs looks a little different than ours, right? And that's okay. So they went from decreasing to increasing to decreasing to increasing. And that's okay. It's okay that theirs has different points than ours. The only thing that really matters is that we, have the correct points of inflection, and we do, judging by what they have here. And we have the correct minimums and maximums. Everything else can be left up to your judgment. So you guys are going to do this one. All right, so after the video today, you guys can work on this one. I want to do this one with you guys, so G we'll do together. All right, if it's okay with you guys, I'm going to go a little bit faster for this one. So hopefully a lot of those properties on the last one kind of made sense since I was going a little bit slower. And then now that we're going to be doing multiple problems, hopefully the repetition will help you to, grasp a lot of the concepts that we're going to be looking at. So for this one, let's look at the first derivative first, which is given to us. Again, first thing I want you to do is find the zeros. There is a 0 at 0. So I'm going to make my little chart over here, my little number line. There's a 0 at 0. And I'm going to highlight the different parts of the graph. I'm going to highlight positive versus negative. So over here, I have negative values. And over here, I have positive values. So on my little number line up here, I'm going to put negative values to the left of 0 and positive values to the right of 0. And again, hopefully your brain is already churning and figuring out what that means. But again, because the sign changes, it changes from negative to positive. That means that this is going to be a turning point. So we already know it has a horizontal tangent, but we can even go a step further and say that it's going to be a turning point because the sign changes. And we know that it's going from decreasing to increasing. So the original function is going from negative slopes to positive slopes, or in other words, decreasing to increasing. That's what this graph will tell us, right? So that kind of helps us to figure out, what this function is going to look like. And then just like in the last problem, I also want to look at the concavity of this function. So if this is the first derivative, to find the second derivative, we're going to be looking at the slopes here. So notice that the slopes are all, and I'll draw some in so you guys can see them. The slopes of these tangent lines are all what? I know it's kind of weird now that I just drew in a bunch of them, but what do you notice about the slopes of all the tangent lines, except for this one that I drew kind of poorly in the middle, but it's supposed to be 0 there in the middle? All of these tangent lines have a slope that's positive. And again, we know that because this entire function is increasing, for the exception of this one point. This point right here has a horizontal tangent line, because look how it gets kind of flat in the middle. So this part actually has a horizontal tangent line, which means that it's going to equal 0 on the second derivative. But the rest of the function is all increasing. Okay, so if the rest of the function's all increasing, that means that it's concave up the entire time, except for right here at 0, and at 0 there's kind of a weird point in there. So if I draw this on a number line, I have a weird 0 at 0, but to the left and right of 0 it actually happens to be positive because the entire thing is increasing. So it's increasing here, the slope is positive or the derivative is positive, and it's increasing here, the slope is still positive or the derivative is still positive. Now again, this 0 here means that the graph has a turning point and it turns from negative to positive. This 0 here means that the graph only has a point of inflection if it changes sign, but notice that it does not change sign. So it's going from positive to positive, which means that this is actually not a point of inflection. So I'm going to write not a point of inflection. And again, that's because it does not change sign. If it changes sign, it will be a point of inflection. But because it does not change sign, then it is not a point of inflection. So from here, you might be kind of wondering, what our possible f of x is going to look like. And one of the hints, and I believe, again, I'm sorry, but I think I only gave this hint to my fifth period class. One of my hints is that if you look at this function and you try to figure out, what function this could be, it might or might not look like this to you, but to me at least, it looks like an x cubed function. So if I know that the derivative looks something like an x cubed function, yesterday we talked about how if the derivative is x cubed, the function above it, remember how it always gets knocked down a power? You always bring the power down front for the power rule to find the derivative. If this is x cubed, that means it got knocked down a power. So the original function, f of x, must have been x to the fourth power in order for it to get knocked down to x to the third power. And again, it would have been 4x cubed, but we don't really care about the coefficient. We care more about what the power is looking like. So the original function probably looks something more like a fourth function or a fourth degree function. Do you guys know what a fourth degree function looks like? If you do not, it kind of looks like a parabola actually, and sometimes weird things happen in the middle, but for this one, nothing weird is happening. It's just going, negative then positive, which means it's going from decreasing to increasing, just like a parabola, and it's not changing its concavity, just like a parabola. The only difference is that this one actually gets a little bit flatter, all right? This one gets a little bit flatter in the middle, so when we actually draw our graph, it's going to look something like this. And I know my graph is not that great, but this could be a graph of x to the fourth. It looks a lot like a parabola. It goes from decreasing to increasing. So our first, just like our first derivative said, it went from negative to positive. Our function goes from decreasing to increasing. It has a turning point at 0, and it's concave up the entire time, which is true about this graph. And again, I'll show you what the book says their answer looks like. So yeah, look here, this is their possible graph. So it looks a lot like x squared, and again, the only difference is that right here, it gets pretty flat for x to the fourth. So the higher that power is, like x to the fourth, x to the sixth, x to the eighth, they all look like parabolas. It's just that it gets flatter and flatter and flatter every single time you add another exponent to it. And it's all even exponents that will look like this. All right, so, oops, that's not what I want. Here we go. We did 2 examples, and that took a whole 23 minutes. We're going to look at 2 more, and we'll see if we can do them a little bit faster. But what I want you guys to do is to remember that I want you to go back after this video is over. And if we don't finish it in class, that's okay, but I want you to do it for homework tonight. And I want you guys to try F, and I want you guys to try H. So try to draw a graph of what those look like. And then I think what I decided actually is I'll just show you the answers when I come back on Thursday. If you're not here, I already told a couple people, I know that Colony Commemorates is going to pull a lot of you guys out. So I already told some people that I will record the lesson on Thursday. I just expect you guys to watch it that night. So you'll see the answers that night. You guys can compare them then. So we have 4 examples within this example 3. This is a new example. It says example 3, we have A, B, C, and D. So of these 4, again, I think I'm going to have you guys try 2 of them, and I will do 2 of them with you. So if we have A, B, C, and D, I will do B with you, and I will do D with you. And then I'm going to have you guys do C on your own, and I'm going to have you guys do A on your own. So let's look at B first. So these ones are a little different because all of a sudden we're throwing either asymptotes at you or, Like in this one, we're throwing a vertical tangent line at you, and this one we're throwing an asymptote, and this one we're throwing not really an asymptote, but a sharp point, and then this one we're throwing in a piecewise function. So these are just different cases that you'll see. So I'll cover 2 of them with you, and then we'll see if you guys can do 2 of them on your own. The steps are pretty much the same. Obviously, we'll get to the ones that are a little bit different. But the same thing I still want you to do is I still want you to look for those zeros, because these are turning points. Or at least they're possible turning points on the graph. It just so happens that these ones actually are turning points. Because if you look at the signs, this is negative down here. Here, I'll make that a little smaller so we can differentiate between the two. This piece is negative here, and this piece is negative here. And then on the other sides of those, you guys can see that they change over here to positive and positive. So obviously these are turning points because their signs are changing from increasing to decreasing, and then vice versa from decreasing to increasing. Now, what I want you guys to notice about this vertical tangent line here is I want you to notice something about the slopes. The slopes here are positive, and they're getting less and less and less positive, so notice how they're going down, okay? All of a sudden we get to a turning point, and then our slopes become negative. So our original function is increasing, right? Increasing, 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 but getting less and less and less steep. Here it turns, and then it starts decreasing, and all of a sudden notice that it shoots way, way, way down, and it's going towards negative infinity. So my slopes are going towards negative infinity, which means that my f of x slopes are going towards negative infinity. Or in other words, the graph is getting really, really, really steep with a negative slope. So it's decreasing and getting really, really, really steep. The fact that there is an undefined point here tells me a lot about the original function. You guys can kind of see in just a minute what it is. But because there's a vertical tangent line here, and notice how the graph is following that vertical tangent line right down, the same thing's actually going to happen over here. We're going to get a vertical tangent line at 2. I'm sorry, when I say tangent line, I meant asymptote. We're going to get a vertical asymptote at 2, and the graph will follow it way down. So it'll be decreasing, and it'll have a negative slope. So you guys can see kind of what that means. So I'm going to start there with my asymptote. So let me draw my asymptote at 2. Oh, that one kind of is not very good. Let's try that again. Oh my gosh. Sorry, I guess I'm looking at this in a weird way. Alright, don't judge. That's as good as it's going to get. So if this is an asymptote, I'm just going to erase some stuff so that it looks like an asymptote. So again, red means the original function is increasing. So let me just draw a little thing down here. There is a turning point at, what is that, like 1.5? And there's another turning point at 2.5. And there's a vertical asymptote. Oh my gosh. There we go. There's a vertical asymptote at 2. And if we look at the values around these, everything to the left of 1.5 is positive. Everything in between 1.5 and 2 is negative. Everything in between 2 and 2.5 is negative, and everything to the right of 2.5 is positive again. So this means that it's increasing, decreasing, decreasing, increasing. Now, that's for the first derivative. For the second derivative, remember we're looking for where the original function is concave up and concave down, and we can tell information about that given the first derivative. So if this is the first derivative, remember, we're looking for the slopes of the tangent lines at different points here to figure out information about the second derivative. So notice that the slopes of all the tangent lines on this piece, because it's decreasing, they would all be negative. So that means that this piece of the graph is concave down. And then over here, all of a sudden it's increasing, which means all of these slopes are going to be positive, which means the graph is concave up. And the point of inflection, quote unquote, is at 2. Now that's not really a point of inflection because there's a vertical tangent line there. It's not really a point of inflection because it doesn't even exist on the graph. But just know that everything to the left of 2 is going to be concave down. Everything to the right of 2 will be concave up. So when I draw this, I'm going from increasing to decreasing with a turning point at 1.5. So from increasing to decreasing, turning point of 1.5, and it's concave down. It looks something like increasing, oops, too high. Increasing to decreasing, concave down, and notice that it follows the asymptote. And again, I know that because my derivatives here are all getting very, very negative very, very fast, just like the derivative graph is getting very, very negative very, very fast. And then everything to the right of 2 is negative then positive. That means that it's decreasing then increasing, and it's concave up. And it has a turning point at 2.5. So it's decreasing, 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 and then increasing, concave up. So notice here at 2.5 I have a turning point, and it was decreasing before that and increasing after, and it was concave up. So my graph looks something like this. Obviously this is not a perfect graph, but you guys get the point that it looks something like that. And again, here's what they put as their answer. So you can see their answer is somewhat close to ours. Maybe ours is not perfect, but it's good enough for what we have going for us right now. All right, and then the last one I want to do with you guys today. So again, just to reiterate, I'm going to have you guys go back and do part A on your own. We just did part B together. I'm going to have you do part C on your own, and then I want to do part D together right now. So first thing I'm going to look for is zeros, because zeros hopefully mean turning points. So there's a 0 here, there's a 0 here. This is above the x-axis, this is above the x-axis, so those parts are increasing. This is below the x-axis, this is below the x-axis, so those parts are decreasing. So when I do my little chart up here, I know that I have a turning point at 0. I have a breaking point. Notice that there's a huge break in my graph at 1. And over here I have a turning point at, looks like 4.5. So for my signs, to the left of 0 it's positive, to the right of 0 it's negative, to the left of, to the right of 1 it's positive again, and to the left of, to the right of 4.5 it's negative again. So I go from positive to negative to positive to negative. So my original function goes from increasing to decreasing to increasing to decreasing. So it goes up, then down, then up, then down. Now, concavity. Yesterday, we talked about how straight lines don't actually have any concavity. So this piece does not have any concavity, all right? Well, that's the straight lines of the original function. I'm sorry, I misspoke. Let's look at this really quick. This is decreasing, so let me highlight the fact that this is decreasing. This is also decreasing. Okay, so notice that we're going from decreasing to decreasing. That means the entire thing is concave down with a random jump at 1. So the entire thing is concave down. So negative and negative, because everything is decreasing. So everything is concave down. We go from increasing to decreasing to increasing to decreasing with a turning point at 0 and 4.5. And there's a break in our graph at 1. All right, so notice that the slope from this side is different than the slope from this side, which means that there's going to be a jump in our graph. So, a turning point at 0. Let's just put it right there. We're going to have a turning point at 4.5. Put it right, well, we'll do that part in a minute. So if let's just kind of do this until we get to 1. So we go from increasing to decreasing, and it's concave down. So it's going to look something like this. It's going to go from increasing to decreasing. And then I know there's like a little hole in the graph right here. All right, so again, this is concave down, and we go from increasing to decreasing. So that takes care of this part right here. We went from increasing to decreasing. We had a turning point at 0, and it was concave down. All of a sudden at 1, there's some break in the graph. Okay, so these points are not meeting. In other words, the derivatives do not equal each other. Because obviously the derivative here is going towards -2, and the derivative from the other side is going towards +4. So if this derivative is going towards -2, and this derivative is going towards +4, that means that we kind of have a break in our graph, that it's not differentiable. So, at this point, we can say that we have another turning point at 4.5, and we can kind of just connect the dots wherever we really want. As long as it's concave down and it's increasing up until 4.5 and decreasing after, then you can kind of just connect those dots wherever you want. We'll just make this a closed circle right there. So both of these pieces are concave down. You can see that from what we've drawn. And they follow the pattern for the first derivative, where it's increasing, then decreasing, then increasing, then decreasing. So positive, negative, with that breaking point at 1. All right, why don't you guys go back and finish example 2 and example 3? Oh, let me show you, by the way, what they had in there. This is what they had for theirs. All right, so you guys can kind of see where they got that from. Looks similar to ours. Concave down, increasing, decreasing, increasing, decreasing. So here's what you guys are going to do. You guys are going to go and finish the parts we did not do together. So we didn't do F, so go back and do F. We did not do H, so go back and do H. We did not do A, so go back and do A. And we also did not do C, so go back and do that one. And I will have the answers for you on Thursday if you're in class, and if you're not in class, I will have the answers for you in the video that you're going to watch on Thursday night. So spend the rest of the period, and whatever time you don't get to finish in the period, take home and finish it at home, and then we'll talk about it on Thursday.